All right, everyone. Welcome to today's presentation of the DBA Fundamentals Group. Today, we're focusing on encryption with Steve Jones, the man, the myth, the legend. In the top right-hand corner of the screen, you'll see the three leaders of the DBA Fundamentals Group, Steve Cantrell, Shane O'Neill, and myself, Kevin Wilkie. And you'll see to our right of our names is our Twitter handles. If for whatever reason you need to get hold of any of us, for example, if you want to be presenting at one of these fun presentations one day and you have an idea lined up, it'd be a great way to send it over to us. You can also reach out to us on Meetup, which is probably one of the ways that you came to this group in this presentation today. Below that is the dbafund.org website, where you can see any of our past presentations as well as any of our future presentations that are set up to go. Below that is our version of YouTube, the dbafundtube.com, where you can sign up to actually be told of when these presentations are available for you to view, and you can watch any of our past presentations. On that note, be sure to sign up and subscribe to our channel today so that you'll be notified whenever Steve's presentation is ready to go and ready to watch. Below that, you can actually reach out to us on DBA Fund, which is our Twitter handle. So make sure to do that so that you'll know when our presentations are coming up. We'll notify you there. You can also reach out to us on our Slack channel or our LinkedIn channel. On that note, today's session is going to be recorded and will be available within 1 to 2 days on our channel, dbafundtube.com. On that note, please make sure to mute yourself if you're on our channel on today's presentations, so that we won't hear any feedback from that. So on that, we go to Steve. Most of you know Steve. If you've been around SQL Server for a while, he sends out great emails and whatnot every day, just about. So we learn all about it. And with that, over to you, Steve.
All right. Thank you very much. All right. Let me share my screen. Well, welcome everybody to this presentation. I'm talking about the encryption primer today, and I put this together a long time ago to help people understand what encryption really is and what does it mean as far as SQL Server goes. So this is kind of an overview of a number of items in SQL Server. Let me advance this. We'll talk about kind of the suite of encryption options there are. I'll demo some of them. It's not too deep because there's a lot to cover in here, but I do want to give you an idea of kind of what encryption is and how it works inside SQL Server. So with that, we want to see the options. The TDE setup is one that I do tend to go through because you encounter it and you don't want to make a mistake really there. And then talk about what different ways we would actually encrypt data with keys and how it might work for us. As Kevin said, I appreciate the introduction. My name is Steve Jones, and my slide looks a little shrunk here, but that's okay. I've been working with SQL Server a long time, most of my life. Over half of it has been as a DBA or developer or manager or writer, speaker in SQL Server. Worked at a lot of different companies in my career, big and small, with different industries throughout the time. And I've seen some good practices, bad practices, and I've certainly had to deal with lots of different security issues in that time. I also founded SQLServerCentral, 20 years ago now, just about, and I've run it for most of the time that it's been in existence. I had a few partners, and they eventually left, and Redgate Software bought my company, and so now I work for them. And I'm a Microsoft Data Platform MVP as well. My contact information is down there at the bottom, and I'll have it at the end too. So if you've got questions, please feel free to reach out. So Kiana, with our agenda, let's get going and let's talk about what encryption is. So I often, do this in person. Hopefully, I'll get to do it again in person and see some of you. But usually, I would ask, does anybody know what this machine is? a lot of you might have seen it. It's been in movies and different things. But this is actually the Enigma machine from World War II. The Germans built this machine to help them encrypt messages. And at some point, the British got a hold of one of these, and it would enable them to break down the encryption. It's a kind of a fascinating machine and how it works. And also, there's some neat stories around it. But encryption is really the process of taking something we can read, like this text we have seen on the screen, and turn it into something that we can't easily read. And we do that through some sort of algorithm or a cipher that will create this unreadable text, and then decryption will be the process of reversing that, taking the unreadable text and making it readable. As an example, you could take a simple cipher where I might do substitution. For example, I could take every letter listed on the top, and instead of that letter, I would use the second line and put that letter in its place. And if you did, you would get something like the third line, and you could decrypt that if you want and figure out what it actually means or what it says. These are the simple types of ciphers that we do as kids, we might have used, but they're not very good for computers because we could crack this pretty quickly. There's the decryption there. More complex encryption would be something like this, which I'll show later, where I'm taking a plain text item, my salary is $1, and I end up with something much more complex like this string here at the bottom. Okay? And that's what we're really doing, is running the data through some sort of function, and then we're getting something different back. So what does this mean for SQL Server? What are the types of things that we can do? Well, SQL Server is not used by itself, right? We have a larger set of, devices or nodes that would communicate or be a part of this. So if you start on the left here in the bottom side, there's a client and a client file system. So right now I'm presenting this system, I'm presenting this code. I've got a client here that's running. There's a file system behind this client, whether that's physical instance, a virtual machine, a container, whatever it is. I've got a client that does stuff. When I want to talk to a SQL server, I would send a communication over to an instance, which is a wire, a network connection of some sort. The SQL Server instance actually is made up of a number of different items. So the SQL Server has memory, where certainly some data, some code, some items live in memory. There is data in the files, right? We have SQL Server data files, transaction log files, et cetera. And then we have backup files as well, where we keep copies of the information that was in our database. So we have this large system where we move data around. And as we do that, we got to understand that we can't do anything about the client file system, right? Anything that we send to the client, they could end up sticking it in their file system, and we can't protect it. As a matter of fact, they could even copy and paste something off their screen into a file, and we would completely lose control of that. The story that I like to tell here is a long time ago, when I was early in my career in the early 90s, Intel was building the Pentium chip, which was the 586, and it's the precursor to most of the chips we use today. And it was a huge investment for them. They were really trying to advance the architecture and make money, produce something that everybody would find amazing. And they were really careful with how they let their designers and engineers work on it. So they didn't actually allow a VPN type link from a home machine to their systems for design. The engineers actually had an early version of what we would call a remote desktop, or RDP, where they could log into a machine at Intel. Everything would live at Intel, and they would, do the work there, and just the image of the screen went back and forth to the client. Well, it was an engineer that actually took pictures of this design using a Polaroid camera, if any of you know what that is, and they used that to deconstruct the design and commit espionage and sell that to AMD and other companies as well. So it was a good lesson in that Intel spent millions of dollars setting up this remote desktop link thing back in the early 90s, and it still wouldn't protect them because somebody could take a picture of what's on the screen. So the lesson is you can't protect what's on the client file system, and you can't really use encryption on the client because the client has to be able to view the data. right? So that's something you want to be aware that as I do this encryption, there are some weak links once the data actually goes to a client. We can encrypt the wire, the communication, the network link for sure. We can encrypt data in memory, and we can prevent somebody that may have a rootkit or malware or something from actually reading the data in SQL Server memory. We certainly can also encrypt the data files, and we can encrypt the backup files as well. So we have a fair amount of protection. There are pros and cons to the different ways we do this. So I'll try to go over this. Yes. Oh, sorry. Question? No. All right, I'll keep going. The way that we do this encryption is we use the keys, which are that cipher, that algorithm that determine how we actually do the encryption. So the keys are like a key to a lock. They actually determine whether or not we can do the encryption or decryption of a particular piece of data. And they work in a hierarchical system, meaning that one key often protects another key. So we not only can encrypt data, but we can also encrypt another key to protect it, to protect somebody from reading it. And so this is a diagram from the old books online. I think it's still in the MS Docs there as well. Kind of, it starts at the Windows operating system, but really that's the base, right? This diagram is somewhat upside down, but there's what's called an SMK or service master key at the Windows level that protects everything. There's a database master key. There's a service master key actually next in line. That's an instance level key. And then there's a database master key and another keys down here as well. And these work in a hierarchy. So it's like over from top to bottom. The top key is actually protecting the next key, which protects the next key, and so forth. The PW boxes are passwords. So in some situations, we can kind of bypass the encryption and just use a password instead of another key to provide protection. I think as we go through the demos, this will make a little more sense, but this shows a lot of options and how things work. Even though we've added some new capabilities in encryption, this still somewhat applies for the setup, either on the client or on the Windows side. On the Linux side, there's something similar to the SMK. It's not using the Windows Data Protection API. It's using a Linux API, but it still exists there as well. All right, so let's talk about communications. We can encrypt the connection to SQL Server, encrypt the network line, and we have a couple of options for doing it. Inside of SQL Server, they actually have SSL encryption built in. So you can put a certificate on your SQL Server and enable SSL encryption, and then the clients would have to have a copy of part of the certificate so that they could communicate back and forth with SQL Server. This actually works the same way as your browser communicates with Amazon or Google, whoever, when you have the HTTPS encryption. It's the exact same thing, but you have to do this for each SQL Server, and you have to manage their certificates. So it's not really recommended because it adds some administration overhead. It's not necessarily more protection. Instead, as long as we are working with clients, which could be application servers or clients inside of our networks, IPsec is what's recommended. Now, IPsec is a lower level encryption in the network stack, and it's set up at the Windows layer or the Linux layer or the Mac layer, I guess, in the operating system, where they're encrypting the IP packets as opposed to the TCP packets at a higher level. If you're not really familiar with it, it doesn't really matter. The important thing to remember here is that IPsec is preferred over SSL. Now in SSL, as I mentioned, you create a certificate. The certificate has to be a valid certificate based on the instance system time. Now, certificates are mechanisms we'll talk about a little bit later, but they have an expiration date on the certificate. And in order for SSL to work, these have to be valid. If I use certificates for other encryption mechanisms, they don't have to be valid because I can't lose access to data. But in terms of network communications, because they're real time, they do have to be valid. Now, I've highlighted in here, don't use self-signed certificates. The reason is that a self-signed certificate could be impersonated because the client has no way to validate the certificate is actually you. So if I create a certificate that says that I'm Steve Jones and this is my SQL Server, you have no way as a client to validate that it's actually the certificate that I sent you, as opposed to another certificate that a hacker or a criminal has inserted into the process. If you've ever looked at security, there's things called man-in-the-middle attacks where you, in essence, insert a non-privileged system into the network communication line. It's not. It sounds like it could never happen, but it does happen all the time. So when the certificates are self-signed, meaning that I just created it myself, there's no way for the client to actually validate it. The way that your browser actually works, or the way that this works in SQL Server with a signed certificate, is that there's a chain of trust, meaning that my certificate would have a code in it that says it was issued by Google. And then Google would say, yes, we validate the certificate. Most clients have a way to actually then double check with Google that the certificate is valid. And that's how your browsers work, that they know that there are certificates from Google and Microsoft and eTrust and Symmetric and various other authorities, and it can use those built-in certificates it has to validate that it's communicating with the system it thinks it's working with. It's a lot of technical detail there. Important thing you need to understand here is that A, you need a valid certificate. B, it can't be self-signed. If you're going to use SSL communications, you need to buy a certificate from a recognized authority, or use something like Let's Encrypt. If they would give you a certificate that was for non-browser use, then you could use that in SQL Server as well. I don't demo this because there's not a lot to see here in terms of trying to figure it out, and it's a little bit complex in setting it up. But keep in mind, if you could avoid this, you really want to use IPsec or another network mechanism rather than SSL. All right. Any questions? We good?
So far, we're good.
All right, let's keep going then. So transparent data encryption. This is, it's been an interesting evolution of this. It's pretty common to use this now. Azure, AWS, most places are just using it by default at this point in time. What the purpose of this was to introduce an encryption mechanism that would help satisfy PCI regulations and similar regulations without requiring you to change all your application code. That was really the idea. So in 2008, TDE was released as part of SQL Server to protect all the data at rest, meaning that the MDF, the LDF, the NDF, and the backup files were all encrypted. So for those of you that remember working in the early 2000s, we had problems where people would lose laptops at airports, or backup tapes or drives would be lost or stolen, and people could just decrypt the data. They would attach the backup file or the MDF back to a new instance SQL Server and read all the data. This was designed to prevent that from happening. Now, there were a number of issues. Some of these have been slightly mitigated a little bit over the years, but IFI was not supported, and I think it's still not supported. The transaction log is encrypted, at least over time. Initially, there's still a problem where part of it is encrypted, part of it is not. Backups are encrypted, which could eliminate compression, but they've mitigated that in later versions. TempDB is encrypted, but non-MDF, LDF stuff, so like file stream data, things that are replicated, this data is not encrypted. So there are not really holes, but limitations in how this works. Now, it's not that hard to implement, but you do have to be careful that you've got backups of your certificate, because if you ever have a disaster situation and I have to recover this, I need a copy of that certificate. In Azure and other cloud providers, they will often manage these keys for you. That doesn't always satisfy your auditors. There are some auditors that would say that's not good enough protection because a third party like Microsoft or Google or Amazon has a copy of your certificate, and so your data is not adequately protected. You can, for the most part, bring your own certificate to Azure or to somewhere else and use that. But again, you need to make sure you have a backup, because if you lose that certificate and your database needed to fail over to another instance, or had to do a disaster recovery in another region, and that certificate wasn't accessible in the cloud, you wouldn't be able to restore your data. And Microsoft is not going to help you restore this data. So with that, let me show you kind of how this works. So you should be able to see Management Studio here. You know, I've got an instance of 2019 here. So I'm going to create a new database. Nothing special about it. Move this down slightly. And then what I'm going to do is I'm going to create a table and put some data in it, and then just select the data back. So nothing big. What I'm really just doing is creating a pattern of data here. So I've got my name and I'm going to root characters here. I think somebody's should be muted, so we see. All right, now I'm going to create a backup of this database. Then we can see that, nothing special. Now I'm going to detach this database. So this will leave the MDF and LDF files on disk, but they're not a part of my system. So if I were to refresh this, I don't have that database down here. So let's open up that file. So here is my MDF file. I just modified right now. I'm in Mountain Time, so it's 10:20. You can see this is the hex, and this is the ASCII. So here's my database name that's in here. And if I were to scroll down here, you'll see there's lots of zeros in here as well. And there's various information. If I were to look for my name, what do we see up here? We see my name, and then we see data. All right, this is a row of data in that table. So there's some header and offset stuff here, you know, row stuff. Then here's my data, and then there's another set of row stuff, and then here's another row of data, and et cetera, et cetera. So this is plain text data that I can read. And as a matter of fact, if I were to open up that backup file and look at it, we would see the same thing as well, that we could actually read the data in the backup file. And that was the concern about how things were actually working in SQL Server, that people could read those files. And I need to change this because I think that's the wrong path. Let's reattach it, see if that works, and can I actually read the data? I can. All right. So that's unencrypted. That's a security hole, and that's why TDE exists. Now, there's a lot of arguments about whether it's good or bad, and we can certainly talk about it. But for now, this is the best solution we have to protect at least that data on disk. So I've got a URL in here for how to do this, but essentially, I need to create a master key, which is just a key in my database. So this exists in my master database right now that I've created this. Now I'm going to create a certificate. Again, this is in master, and I'm doing this all in SQL Server. This is a self-signed certificate for this purposes because I'm using it with a known client, meaning a DBA that works at this company. That's fine. This would not be okay for SSL. Then what I do is I create this database encryption key, and I give it an algorithm. As a matter of fact, I think if you can see I have different algorithms available here. At this point in time, really you should be using the strongest thing available with a 256-bit encryption. And this 256 refers to the length of the key, right? So at every point that I add another bit to the key, I double the level of encryption that I have. So this is not twice 128. This is far beyond 128. And then you'll notice that I've protected this key with a server certificate because I'm in the TDE primer database here, that I've given this name to it. So I'm using that hierarchy where I'm saying I have a certificate, and then I'm going to use that to protect this other key, which is this database encryption key. Let's run this. And sorry, my IntelliSense messed me up slightly there. Let's do that again. Now there's this warning that appears. The certificate used for encrypting the database has not been backed up. You should immediately back up the certificate. Please heed that warning, even if you're testing this, because if you blow up this instance right now, after I encrypt something, I would not be able to recover the data. So let's make a backup here. This password is needed to restore, recreate the certificate, etc. So please use something, save it in your vault somewhere that's protected. So now what do we want to do? We want to encrypt the database. So I have this query that says I want to check encryption status, and it's just looking at some DMVs. And what you'll see here is that the is encrypted stuff is set to 0 for everything but tempdb. I haven't encrypted anything, but because I created this database encryption key, SQL Server now knows that any database could be encrypted, so it immediately encrypts tempdb. The encryption state 3 means that it's encrypted and it's set to 256 here. Okay, that's the default that SQL Server has done. SQL Server is managing encryption in tempdb separately for itself. But my TDE primer is not encrypted as of yet, but the encryption state is set to 1 because it does have that database encryption key. So what I want to do is I'm going to run this query. I'm going to then turn on encryption, which is this alter database statement, and then run the query again. Because this database is small, it will happen fairly quickly. So I run this. We'll see that the initial state is set here to what we saw before, the 1. And then right after I've turned on encryption, it's in 2, which means that the encryption is in progress. And you can see the percentage complete here as well. The way this works is that while the database is in use, SQL Server starts writing encryption on the pages. It reads a page, it encrypts all the data and writes it back. But it takes time to do that. It takes physical time. So we don't want to prevent people and clients from using the database. So this is just happening in the background. And if I run this again right now, it should be done. But if in a large database, you could actually check the status over time to see how far along are you and when am I actually protected. For the most part, we don't care, right? Most of us that decide to do this would know that it takes some time. And if it takes a day or two, that's fine. We're just enabling encryption. The important thing to understand is that at this point, your database is partially encrypted until that status hits 3. And so you have to understand that. That also means that if you were to run a backup, it would be partially encrypted. And your log is also partially encrypted because everything that's in the log before you did this is unencrypted. Everything written after this will be encrypted. So your log, until you actually roll through all the virtual log files, is half encrypted and half unencrypted. You just have to be aware of those things. If you have an audit coming up or something like that, and they were to actually look for data, that they still could find it until the encryption is complete. Let's verify that. So I'm going to detach this database again. I'm going to come back over here to my handy hex editor, and I'm going to reload the file, I think. Reload, there it is. So if I reload this file, I still can read the header. This is not encrypted. But as I go down here, right, what I'll start to find is that it looks like there's a lot more encrypted data in here. Right, there's a lot less of those zeros. And if I were to look for my name, I actually wouldn't find it. This pop-up appeared here. And the reason is because that data is encrypted. So even if I knew the location of that file, and it was, I don't exactly know how far down I was, but even if I were to go through here, I would never find that string because this data is now encrypted. And the same thing if I made a new backup, that wouldn't be encrypted as well. Okay. Now, in the script, I make a new backup here. I reattach it and make a new backup. You could certainly run this as well. I've got these scripts available for you. Let me just, that's the wrong file. I just want to do this so that I remember to delete the files later. You can copy the files to a new instance and restore. Okay. I have a second script in here. So that's where I would put that. And then I could check my data and see it. I'll leave that restore exercise to you if you want to practice with it. You have to use a second instance because in general has been seen to be less than 5%. Now, I've got a few links here. A lot of people have kind of tested this. A disk, people are saying around 10% from their testing, which is not insignificant, but it's not a ton considering that it gets you protection from, really auditors. Okay, so this is an enterprise edition feature and is default in Azure, but there are a lot of people that don't think it's useful because they say that a privileged user could get around the encryption. If somebody gets control of your instance, they can get the certificate and they can get, copies of your data and that kind of thing. That's totally true. But as humans and as a DBA and a manager, I've seen lots of silly, stupid mistakes, including, people losing laptops that have copies of the backups on them, or, problems with third parties like Iron Mountain or other services that carry backup tapes off-site. There are always problems here. There are always malicious employees. And so I think it's worth doing. If for no other reason, then it helps you get through audits and it makes regulators and regulatory authorities more comfortable with what you're doing. You can argue about it if you want, but I think it's worth doing, especially at a small level of overhead. So any questions so far on that TDE?
Yes. Which versions of SQL Server is it available in?
Oh, yeah. So 2008 on, right? So 2008, R2, 12, 14, 16, 17, 19, and the 2022. So it's available in all those versions. I believe all the cloud vendors actually support it as well, at least all the major cloud vendors. But it is Enterprise Edition only. Right now, if you use, I don't know if you can actually buy Standard Edition in all the cloud providers, but it is Enterprise Edition because it is a regulatory feature.
Okay. Is there a conflict between RCSI and TDE?
No, there's no conflicts. I mean, they both are adding some overhead there, but there's no conflicts.
Ooh, so this one is my favorite question I've seen asked on it. Tammy says that they were cautioned not to use TDE on the vendor databases. Should you do it anyway, or do you say no? What funness can you happen on that one?
Yeah, so I mean, vendors are always interesting because vendors often don't want to use features that they haven't tested for support reasons, which I understand. There isn't a good reason to avoid using this. Now, there's not necessarily a great reason to use it unless you need to. So if I had a vendor database that was bound by PCI, I would probably push back on the vendor and say, we've got to enable this because it's a requirement for PCI. Now, it's not really a PCI requirement. What PCI says is that you must encrypt and protect data, and your auditor may or may not find this sufficient, or they may or may not find a problem if the vendor says that they're handling it in some way. So I wouldn't go enable this on every database I have, because lots of databases aren't necessarily full of PII data that you need to worry about. But really, you got to push back on vendors if you feel that you need it, or your auditor or regulatory authority tells you do need it. really push back on vendors. So you just need to test it and verify it's not going to break anything, because it's not. I mean, there's no difference to how a vendor application actually connects to the system. So that's what I would say.
Awesome. I think
All right.
that's all the questions at the moment.
All right, so let's keep going. So let's get into hashing. So hashing is the most basic type of, I hate to say encryption because it can or can't be encryption, but you know what it really is it's a mapping function. We use this in computer science all the time. We use it to bucket things into groups. And you know, we have a hash join in SQL Server. And essentially what they're doing, as you see here, is taking some sort of key and I'm running it through a function and then creating a hash of that value, which is typically a smaller value than the original key. And often what I'm trying to do is bucket things together. It's incredibly useful in computer science. Now, in SQL Server and in encryption places, we don't want things to bucket together because the idea is that we want everything to be its own unreadable value. When they come together, we have collisions, right? Because we have two items that hash to the same value. The problem with that is if I were to use a function for something like a password and hash it, and I had a password and Kevin had a password and they both hash to the same value, that would be bad because it would mean that Kevin could log in as me with his password, or I could log in as him with my password because they would come to the same hash value. So in general, while hashing is really valuable in computer science, on the security side, we want hashing to be unique, not bucketing. Now in SQL Server, we have a number of functions to do this. We have checksum, hash bytes, binary checksum. And then we have other items that you could implement with SQL CLR as well. They can be useful or not useful, and I want to show you what I mean here because these are actually some common uses. So somewhere in may not be larger or smaller, but what I'm trying to do is just turn this into some value. Now here I'm going to take a couple of different strings. Algorithms here as well. There's actually a SHA-3 right now. I'm not sure if that's in SQL Server. Should actually look. We can see here, if we look through here, that this and this are different, right? 1 and 2 are different. There's only one SHA algorithm. So when there were more, they actually added SHA-1 and they didn't want to break SHA. So these are the same. But the same string at different key lengths with the different algorithm produces different values. Okay, nothing magic about this, but I'm just producing values. I can also do something else called adding a salt. So if I run this, I should get two different values, which I do. And so what I've actually done here is I have my string, but I have this other value, which I'm calling a salt, which is just another string, right? This is the original value, and here's the values concatenated together, right? The original one plus the salt. This should be lowercase t. I'm case insensitive here, just so you know. And it gives me a different value. And so why is that important? Let me show you a common problem people have. So let's create a table, and let's stick in Steve, my business partner, Andy, and we're going to put in some different passwords here, okay? These are encrypted passwords because I'm using the hash bytes to do a one-way encryption. I should have mentioned that these SHA algorithms, there isn't supposed to be a way to go backwards, right? Which is why these days, no place you create a login should ever be able to give you your password back, because that's a security hole. It's an attack vector. Everybody should be using one-way encryption for passwords. To test my passwords here, look what I'm doing is I'm just going to create a password. I'm going to pass in a parameter. I'm going to encrypt the parameter and then see if it matches what's in the table, essentially. Right? That's a simple type of thing. So if I were to run this in as a routine in my application, right, can I validate my password? Well, I get a match back. If I try a different password here, I should get an unmatched value. Right? It's a common scheme many applications, websites, etc., use for create and lose user accounts. Now, here's the problem with this. I'm going to do a table update, right? Let me actually do this first. I'm going to select this. We'll see that these are different values, correct? Steve and Andy have different values because we have different passwords. Now I'm going to update these, and now we have the same value, right? So what I've done here is I've copied over Andy's password to mine. I'm using Andy's password, but we're checking for Steve, and it works. And this is the type of thing that SQL injection allows, malicious actors to do on a website or any application, is that if they can get through SQL injection and they can find a user table, they don't have to decrypt the passwords. They can just do something like this, copy a password over. So have an account that says like admin or, sysadmin, default, DBA, whatever. Those are security holes because they open you to this type of vulnerability. As a matter of fact, somebody inside your organization could do this and then log in under your account. Okay. As a matter of fact, the way that I check is that my password now fails. The thing to note here is if you're an administrative privileged user in your system and you ever can't log in, right? Like not like you typed the wrong password and you get locked out, but if you're sure you put in the right password and you can't log in, this is a huge immediate security hole and breach that should be flagged right away. And you should be checking to see if somebody might have updated that password because it's a big problem. So first thing I'm going to do is I'm going to reset the passwords here. Now, when I reset these passwords, I actually added a salt. So I didn't just use the password and I didn't use a scalar value. In fact, I used the value that should vary across each row of the table at this point. And so what I'm going to do now is I'm going to update my check procedure to use that similar salt. And now I'm going to check, can I use my password? Yes, it works. Let's hack the system again. Can Andy use his password to log in as me? He can't. And the whole idea here is that we use a salt somewhere. Now, in this case, my password is lost. I would have to reset it, right? Because I wouldn't necessarily know what Andy had done here, but I do this. This could be guessed. So using a salt in the same table is something you want to be careful of. You might use a different table or with a complex scalar value that is only in the procedure so that a hacker wouldn't be able to determine what this salt value is. Okay. Those are the things to take away from that. The other thing is make sure you have one-way encryption, because if you lose a copy of this table, you certainly don't want people to be able to get the passwords back by decrypting that table with brute force. All right, let me clean up. Let me show you something else. Checksum are incredibly valuable in a lot of things we do. Here I'm going to create two values and run checksums. Okay, these two collide. Checksum is definitely not something we want to use for security. And binary checksum is really no better as well. So here you'll see I'm going to use a few different values. These values all hash back to the same binary checksum. So remember, if you're going to try to use hashing and you want to use this for something like passwords or some other type of one-way encryption, be really careful here. Make sure that you have an algorithm that isn't going to create a lot of collisions like this checksum algorithm. And then B, I'm using a strong algorithm with some sort of salt if somebody could potentially do something like just copy over a value from one row to another. I don't want them to be able to somehow break my protection or break my security. All right, any questions? Hashing?
Nope, no questions on hashing.
All right. Summary, hashing is not really encryption. Decryption is not usually supported, but again, right, if I took a dictionary of every baby name in the world, right, or a dictionary of every name and every word, and I started hashing those together, I could create a table that would allow me to try to figure out what the value is. So you want to be careful here. Now, hashing is deterministic. I say encryption is not, but it can be deterministic as well. So, it's hashing is kind of pseudo encryption. The one thing hashing has going for it's super fast. Encryption has notable CPU impact at scale. Hashing typically doesn't. So keep that in mind. Because it's deterministic, can be indexed. So that's a value as well. You always want to use the strongest algorithm. I know the SHA-1 algorithm has been broken. The SHA-2 might have been broken. If SHA-3 isn't in SQL Server and you wanted to do something like this, I actually would build a SQL CLR function that implemented SHA-3 from .NET and do that as well. So, all right, let's keep moving. So here are keys. Let's talk a little bit about the keys. Now, I've said these are part of this hierarchy, and we've got all these different keys here. I want to lightly discuss some of these, and then we'll go into more detail in the symmetric keys and asymmetric keys. So again, here's kind of our hierarchy. Again, passwords could substitute for some of these keys, but the service master key is at the Windows level. And as far as I know, well over 2 decades, the DP API hasn't been broken. Nobody's been able to find a flaw in this. So that's a very strong protection for this key. That is what protects the instance level. And then at the database level is where all these other keys live. This service master key is interesting. There's conflicting documentation that says it's created when you install SQL Server or when you first create another master key. I don't really know how it is in there, but really it doesn't matter. You don't have to worry about it because you don't create it. You don't have to back it up. You don't do anything here. Or sorry, you don't have to create it or deal with it. You can back it up, and you probably should, unless you have a way to restore a server image and get this back. If you can't get this back, you can sometimes override this, but if you're trying to restore this exact server the way it was, meaning I've got database master keys in various databases and I've got other things there, you would want a copy of this. Even with TDE or something else, often you can, if you have backups of other keys, you can get away with not having this. I typically haven't run into any situation where we absolutely needed the service master key, but I hate to, I'm a very conservative, careful DBA or manager, so I would just back up these keys if I've implemented encryption in any instance, just back this up and keep it somewhere, okay? This is fairly strong encryption. This is the AES or blowfish algorithm. The database master key is something you have to create in each database if you are going to use encryption. Now, this is secured by the service master key. It can be secured by a password only. If it is secured by a password only, you will have to manually or with scripting open up each database in order to restart recovery when an instance restarts. The only reason you would want to do that is you don't trust your DBAs. And you've got some third party, some finance or application person that really wants to protect the data in this database. And so they would manually open up the database and enter the password for the database master key and allow it to run. I actually haven't seen anybody that was that concerned about it, but it's an option if you want to do that. There's backup and restore commands, if you want to do that as well. All right. I've got a couple of scripts that show some of the code, but there's not a lot to it. It's basically, there's a create, drop, and backup DDL for those keys. So let's go on to symmetric keys. So a symmetric key is similar to the type of key lock that we often deal with, right? If I have a front door lock, this is my front door, or a padlock, there's one key involved here, right? One key physically opens and locks the door, or in the case of a combination lock, one combination key opens it. It's a physical lock after that, but really there's just one key. And so that's why it's symmetric, because there's only one key involved. Now, these are interesting keys because you create them only in a database, and they're only in that database. You can't back them up, or you can't restore them. However, the key themselves are deterministic, which means if you use the same parameters and the same size algorithm, you create the same key. So that's good and bad, right? But it does mean that now my DDL code to create keys is a security item that has to be protected. If you're going to use these keys and you do best practices like use version control, you might need to actually version control these keys separately from the rest of your code, or at least make sure that that folder or that location in the repo has extra security, because these are now, somebody could recreate that key on their system, and if they got a hold of your encrypted data, they could decrypt it. So it's something to just be aware of. Now, these keys require less resources than asymmetric keys, but it's still quite a bit more CPU than hashing to actually take data, run it through the algorithm with this key, and then produce the encrypted or decrypted data. Now, these keys have a GUID in SQL Server, and if we have the same identity value, we get the same GUID. In any sort of session you're working with, you have to have uniqueness here. I haven't ever found this to be a problem, but just be aware. There's another parameter called a key source. The key source and the identity are used to recreate the key. So those are the two values that now you have to protect, right? That's your security area. While these are secure, you should secure these keys with asymmetric keys, meaning I should encrypt the symmetric key with an asymmetric key. All right, that's typically what we do. The asymmetric key would then be protected by my database master key, protected by my service master key, and then Windows or Linux as appropriate. So let's look at how these are in use. And this is similar to how hashing is actually used as well. Interesting, because I'm now altering code and table here, right? If I were to implement this in an application, I added a value. Here I'm going to create a symmetric key and encrypt it by a password, which is an option. Okay. Now to use this key, I have to open it with that password. Now what I'm going to do is I'm going to, in this new column, I'm going to put in my encrypted data, and then I'm going to remove the old. All right, I think I dropped. Hopefully I'm back. Am I still sharing?
You are.
Okay, good. All right, so what I was saying is I'm going to encrypt this data here. So let's execute this. And then I'm going to set this to 0. So if I look at my table now, the original column is zeros, and here are my encrypted values. And while these look similar to a point, that's because the key name is actually here. So that SQL Server knows which hash is in the key, and then the rest of it's here. Okay. There's a GUID that I use for this. I don't know why this is required, but if I were to do a decryption, I don't need it. I don't know why this is a function there. If I do this, what we see is I don't get the salary back, right? Why not? You have to actually cast this back, right? You have to cast it back to a varchar and then a numeric. And I don't know why they made this difficult to do, but it is what it is, right? Now we can see I have my salary back. This drove me crazy when I first was learning encryption because it's not well documented. Actually, now I should actually submit a note to this MS Docs item that says make sure you cast it back. You'll notice I didn't open the key there. Let's see what happens. Now, my son Delaney is super smart. Like, he's wicked smart. He's the smartest kid in the house, smartest person in the house, actually. He decides he's going to change something. So now if I look at my salary, he's given himself a little bit of a raise here, which isn't what we want, right? That's, I don't want this. My wife would certainly not be happy about this. So then we would know. We have an attack without decryption. This is why, again, just like the hashing demo, SQL injection is a huge issue. Please, please, please don't just use dynamic SQL everywhere. Don't just take unexamined output and use it to concatenate into values as either parameters or queries or anything else. This is the reason we have so many problems in applications, because we can have attacks without decryption, or we can have attacks without functionality. So what can I do? Let me fix this table. I'm going to add a new column here, which is a unique identifier. I'm going to populate it, right? And then let's just look at the data here. Yep. So now my salaries are still there and my row GUID has unique values. So now I'm going to re-encrypt with an authenticator. And what this is, you'll notice I need the key GUID in this function. This, to me, is just really poor software development and engineering. I should just be able to put the name here. I've added this one and then this row GUID on the end. This encrypt, the encrypt by key. It requires, the key GUID, not the key name, silly. The clear text, we'd expect that. Then I have these two optional parameters. I can say 0 or 1 to add an authenticator, and then I add the authenticator as itself. Again, silly software authentication, this is redundant, right? I should just have this here as an optional parameter. This is essentially a salt, okay? So when I look at my data now, it just looks encrypted, okay? But when I decrypt it, in this case, I add the authenticator values back in there as well. Now, if my son tries the same attack, it actually doesn't work this time. What I'll actually do is get a null value, which is nice because it alerts you to the fact that the encryption has been broken somehow, that what I expected to decrypt doesn't actually work here. So if I didn't have the casts, obviously I would still see this as well. But it's good to just note here that this could be a item you flag if I can't all of a sudden decrypt value. Okay. Pretty simple. Again, the hashing demo, the way that works and the way the symmetric keys, very, very similar to how they work together. Right. The difference is this is a lot stronger protection. This is a lot stronger encryption, but it also requires a lot more CPU to run. I mentioned the header has the algorithm in there. You can generate temporary keys, which is an interesting thing. This is a nice workaround that, again, the code now is a security issue, but I'm also not leaving the keys around in the database. So if I had something like a point of sale system in a convenience store, I could generate a temporary key, encrypt data, and then drop the key. The application now has the data needed to generate that key, but the database itself has no way to encrypt or decrypt that data. So you actually have a strong level of protection inside the local database. I could replicate that back to some other headquarters where I could recreate this key as either a temporary or a permanent key and be able to decrypt that data then. So there's some interesting things you can do with symmetric keys here to protect them. If you use a password, keep in mind the encryption is much lower. Triple DES is it's been broken for a long time. If somebody gets a hold of it, they can crack it very quickly. So just keep that in mind. All right, I'm going to keep going. Kevin, let's just hold questions till the end because I'm going to kind of race through this. I know it's running a little bit long.
No worries.
All right. Okay. So asymmetric encryption. This is unlike any physical thing we have. It's very different. And it's based on some very complex math. It was kind of built in, at least the computer side of this was kind of built in the early 80s, maybe late 70s. I can't remember exactly. But it's based on prime number math. It's much, much more secure than symmetric keys, but it requires orders of magnitude more resources. Like if you encrypt everything with asymmetric encryption, you're going to take an incredible CPU hit. The way this really works is that I should have a key 2 here. Maybe I can, yeah, I did there. In any case, can I fix this? No. Where's my pen? I'm just going to fix it here for now because it bothers me. It's a 2. I'm taking text here. I run it through the algorithm with key 1. This gives me text. Okay. Oh, no, that is a 1. Sorry. If I take this text and this text to the same, right? So these two items are the same. If I take that text and I run it through the algorithm with key 1, I don't get the value back. Right. But if I run it through with key 2, which is a pair from key 1, I do get the values back. Okay, so again, this text and this text matched, and this text or this binary value matches this value. So I've got 2 keys is what I'm using here to make this work. The way this works is a private key and a public key. The organization and individual keeps their private key private, but they publish a public key for everybody to see. Okay, you generate them together and you release one. And it sounds crazy, but this is how your browser encrypts stuff in SSL, and this is how a lot of encryption works. So the way that it happens is that anybody can encrypt data with my key, right? This is the value, that anybody can do this data with the public key, but only me or only I can decrypt the data with the private key, and vice versa. Okay, so I can encrypt it with my private key, and anybody can decrypt it. Well, why would I do that? This is signing. This is code signing. This is message signing. This is how we validate that the place from which we got the data is the place we think it is. So typically, I don't really want to explain it all now, but essentially what it would do is I encrypt something with Andy's public key, and then I re-encrypt it, or sorry, I encrypt it with my private key, and then I encrypt it again with Andy's public key, right, in this case. So now I've encrypted it with my key, right, which means that anybody can read it, but you're guaranteed you know it's from me. And when I encrypt it with Andy's public key, only Andy can read the message now. All right, so this two-stage encryption means that I can not only protect the message, but I can validate that it came from a particular person. And so same thing, only Andy can get the message with his private key. Then he can validate it with my public key. So that's how this works. And it's really a cool little system, other than the fact that it requires a ton of CPU. There's DDL to create these keys, or I can create them outside of the server. sn.exe creates just a normal asymmetric key. Makecert creates a certificate, which is an asymmetric key with metadata around there. Okay. I can create these with passwords, or I can set it up so that I wouldn't need it. But typically you would want a password here in some sense. And then what I'm doing here is I'm providing extra protection because I'm only using the asymmetric key to protect the symmetric key. So I only take that huge CPU hit once. Okay, so I'm balancing security with resources. And then I take a medium level of CPU hit to decrypt data with this key. Okay. As with the symmetric key temporary keys, I could also remove the private key from the database, which prevents decryption in that database. So only the public key would be there to encrypt data, but I couldn't decrypt it because of the private key. So again, this is a security mechanism where I might have a semi-secure system where I want to protect data, but I don't want to decrypt it because I'm not 100% positive I can keep it safe. I would then replicate that data out to a different system that would have this private key. Certificates are certificates, right? Whether they're used for web servers or SSL or here, they're just certificates. They have this metadata with an expiration date and a subject and some other data in there as well, okay? In this case, the expiration date is not enforced by SQL Server because I would not want to lose access to data. This is not the case with SSL. It absolutely is enforced there, okay? If I'm rotating certificates, right, there's a few things I can do. One is watch for this expiration date here. The other thing is that I need to decrypt and recrypt the data that I'm using. In this case, it would really be the keys that I'm using here to do the rotation. There is no restore. We use create certificate instead. SQL Server 2012 increased this length. I don't think it has increased since, but always go along. Okay. I'm just going to lightly show this demo here. I don't want to spend a lot of time here, but here's how I just create a key, right? This doesn't work right now. And the reason is Microsoft's actually deprecated these because 1024 has been broken. So if you can set database compatibility level to actually use this, but please don't do that. Just please use 2048. 2048 just works, okay? How this would work, I'm just going to do this, right? I'm getting encrypted value and decrypted value, just like I did for the symmetric value. I could actually take this value and just stick it in this string and decrypt it as well. There's nothing magic here. Okay. The other part of this, demo, I used to show make cert. Make cert is in the Visual Studio SDK or .NET one, I forget, but I could do this outside of SQL Server. I could then load it into SQL Server here by doing a backup. Well, sorry, not a backup. I would do a create here to restore this, or I could do a create with whatever certificate I created here. I could do that as well. All this does here is I'm using this password, and then what I would do is typically in the places where I use it, I would just add encryption by certificate as opposed to encryption by password or encryption by passphrase. The demo kind of runs through something similar as I did in the other demos. So there's nothing magic about this. It's really just function calls. I want to spend just a couple minutes here on always encrypted because this uses the asymmetric protecting a symmetric key mechanism. And it's something that actually is really good in a lot of ways, especially in 2019 and beyond, where they've added some additional features. So in 2016, they actually added this. And the idea was to separate keys from client and server, so I didn't have this single point where I could get into trouble with encryption, and also avoid changing code. Now, I had to change drivers, but I didn't have to change code. In 2019, we actually added a third server you could use for attestation, and I'll talk about that in a second. But here's the marking diagram, and the idea here is that my application sends a query through the driver. Now, the driver actually then will do a check to say, am I querying something that's encrypted? If so, there's actually another round trip in here because what it says is that there's a column encryption key in use here, and I need that key. So what happens then is it says it sends the encrypted value here. The client gets this column master key on the client, uses it to decrypt a key and send it back over here. And then SQL Server can use that decrypted key, it doesn't send it back. It holds it in memory. The encrypted data here gets sent back, and the driver does the decryption. And then we would see the social security number of 1, 2, 3, or whatever it is would exist here. So in this case, the encrypted, there's this firewall here. So the encrypted data is always on this side. The decrypted data is only in the client. There's situations where I trust a client and I don't trust the SQL Server for various reasons, including in a cloud provider. This is very valuable to do that. I also break that CPU load and I spend it mostly here on the trusted client side or trusted app server side, as opposed to the single point of failure and resource usage on the SQL Server. Okay. There's a certificate involved here, and there is a symmetric key here that's encrypted. Okay. I know I've made a mess of this diagram, but it's actually a very neat system for doing it. The hassles are, if this stuff is random, I can't index it very well, which means that joins don't work. Now in 2019 and 2022, I can actually have a protected area of memory here where we can send the key back and this data would go in here and get decrypted. And then we would be able to do joins and matching in here on decrypted data, which could improve performance. It's a really neat system. Cryptologically, it's secure because that third party attests to the security of this memory space in here. So I need certain hardware. Wow, I don't know why I think Teams is doing this, but the third server is linked here to say that I will validate that this server has protected areas of memory and that I give you a secure way to decrypt data. It's a really fascinating system. There's a lot you can read about the attestation server. At least in 2019, it had to be a data center level server, not a enterprise Windows server. But it's a neat system that provides protection and improves performance as well. If you're in 2016, 2017, then you're really stuck here. And I can do deterministic encryption for indexing purposes, but only for certain types of queries. There's a lot of restrictions, a lot of interesting things about always encrypted that mean you really want to be careful before you use it, but you don't have to change your code necessarily, which is kind of interesting. You do have to change the collation of those columns, but I don't know if we have encrypted data, most of us care. The last thing I want to cover here is on key length. In 2012, somebody attacked Gmail. They made there's this DKIM type of record we have, a certificate. Somebody broke that in 2012. Okay, and it was a big deal because for a while Gmail was slightly insecure. A 384-bit key could be cracked on most high-end laptops today. If you have an i7 or a Ryzen or something, you could do that. I've got a link here. 512-bit key, 512-bit certificate can be cracked in Amazon for about $75. You can borrow computing resources and do that. It might be cheaper today even. The 1024-bit keys have had issues. So the point is this stuff changes all the time, but you should always go with the longest key length you have. If you care about security, just sacrifice the CPU, buy more cores, whatever you got to do to protect the stuff you need. Okay. I'm going to skip this. This was kind of a quick demo of always encrypted. I think I just had it in the wrong slide place, but you could just walk through that in the slides if you want to download them. Hopefully I've covered these goals, give you some idea what's going on. If you've got questions, please let me know. I'll send Kevin the Git repo link for this. Actually, I could just pull it up, I guess. And send me those things. Where's my Git repo? Let's pull it over here. It is not there, but we have to go to way out west. I was just in it. Well, let's do this. There. If you go to github.com, way out west, there's an encryption primer repo. Okay. All these setup files are here and the PowerPoint is there as well. So you can download it. You can see there's a couple of animations if you want to look at those, or you can just flip through it. And then there's resources at the end as well. And other than that, if you've got questions or something, please feel free to get a hold of me. Any questions, Kevin?
No questions. I'll make sure to put this, the Git repo out there for everyone to enjoy along with the recording.
Excellent. Excellent. Well, cool. Well, thank you very much for having me. Hopefully you enjoyed it and learned something. And let me know if you need me to come back at some point in the future.
Oh, you know it, Steve.
All right. Well, cool. Thanks, everybody, and have a great day.
Thank you so much. See y'all next time, y'all.
All right. Cheers.